Hello everyone, this video is entitled Bohr's Atomic Model. In this video, I explain how Danish physicist Niels Bohr used emission and absorption spectra to significantly propel forward our understanding of the atom. I discuss the successes of Bohr's atomic model and its limitations. I also make clear why knowledge about the electron configuration of atoms is considered to be so important. If you have not yet watched my video on emission and absorption spectra, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started.
I'm going to kick off today's lecture with the idea of electron configuration. So electron configuration is the arrangement of electrons around an atom, a molecule, or a physical structure. It is concerned with the way electrons can be distributed in the orbitals of atoms or molecules. It's a very important concept. And really the question is, why is it so important? Why is it that so many scientists at the turn of the 20th century spent so much of their time and effort trying to figure out how electrons are arranged around an atom? And really the answer to that question is to clearly understand how atoms behave. It is by understanding where electrons are around an atom that we can better understand why atoms are actually interacting with one another and why specific atoms will chemically interact or chemically bond and why some will not. It also gives us a formal understanding of the structure of the periodic table and how we could better arrange these elements. The concept of electron arrangement was first conceived by Niels Bohr. He was a Danish physicist. Now, in today's lecture, we're going to discuss the Bohr model. But in fact, you guys might know it by another name. It's the Bohr-Rutherford model. Now, it's important that we actually give tribute to Ernest Rutherford. It was his model that the Bohr model was scaffolded onto. It was the beginning of the Bohr model. And so Ernest Rutherford, his model was essentially the idea that we have a central nucleus and we have this vast cloud of randomly distributed electrons around it. And in fact, we know now that those electrons are not randomly distributed around the nucleus. Okay, so he just thought it was this random large cloud. And he came to that conclusion from his very famous gold foil experiment. But Niels Bohr, he actually used the information from Ernest Rutherford and all of that spectral data for atoms that we discussed in the last lecture. So the emission spectrums and the absorption spectrums to come to his formidable conclusion that we now call the Bohr-Rutherford model or the Bohr model. Okay, and so let's go to the next slide to see what that model actually is. Okay, so Niels Bohr used the absorption and emission spectra of elements to conclude that the only way you could have bright lines and dark lines in the exact same spot for a particular element each time you ran an experiment was if the electrons of that element existed in fixed positions around the atom. The idea that each electron would absorb an exact amount of energy and release that energy as a photon that would then hit a detector plate in the exact same position each time you ran the experiment caused Bohr to believe that those electrons could only exist in certain places around the atom. He called those places orbitals. And of course, these ideas are strongly supported by Max Planck's theory of the quantum. Remember, he stated that each particle of light can hold a specific amount of energy within it. He called that amount of energy a quantum. And so, the assumption that each electron could only absorb or emit a certain quantum of energy caused Bohr to come up with these ideas of energy levels. And so if you look at this image on the right here, this is a perfect depiction of Bohr's model. Okay, and so he created each one of these energy levels represented by the specific numbers n equals 1, 2, 3, etc. And he actually labeled each one of those rings, each one of those orbitals with a specific letter. So K, L, M, N. And so for the sake of simplicity, I'm going to go over some details with you guys. So the idea of energy levels, shells, and orbitals being used interchangeably is quite all right. In fact, all of them mean the same thing when it comes to the Bohr model. And of course, each one of those shells, orbitals, or energy levels are represented by circles in a two-dimensional model. And the maximum number of electrons per shell or per orbital is 2 times n to the power of 2. And of course, n being the number for that orbital. So if you're in orbital 2, it would be 2 times 2 to the power of 2. Okay? So what are Bohr's conclusions? Bohr concluded that electrons cannot change energy in a continuous way, but in discrete ways, in discrete amounts. And so you're not going to have a steady transition of an electron from one orbital to another. No, you're going to have that electron spontaneously jump from that first orbital or second orbital that it's in to the third or fourth orbital, whichever orbital it will transition to. What's more, he says that an electron cannot exist between energy levels. So the analogy I have here is a ball sitting on a flight of steps cannot exist between steps, okay? So when you throw a ball down a flight of stairs, you're not going to see it kind of hover in between two steps. That never happens. And so the same thing does not happen with electrons. Electrons are only going to exist in their distinct orbitals. And so you're not going to have that steady transition. You're going to have it jump specifically from one to the other. Okay? So this picture on the right here is of the dashing Niels Bohr. In fact, I think this picture was taken immediately after his discoveries were published in 1913. Good looking guy. So, we're going to talk a little bit about the assumptions that Bohr had to make for his model to work. His two postulates. So the word postulate is just a fancy word for assumption. And so Bohr's first postulate, an electron can exist indefinitely in an energy level without losing energy. And so what does that mean? Basically what he's saying is electrons circle around the nucleus of an atom without actually losing energy. They do so just like planets circle around the sun. Earth is not going to slow down and stop in the middle of space, just like an electron will not slow down and stop when circling around the nucleus. In fact, the reason why it circles around the nucleus is because of attractive forces, just like Earth circles around the sun due to gravity. And so each orbit corresponds to a state of constant energy, and we call that state of constant energy the stationary state. His next postulate, the second postulate, is electrons can jump. Transition is the scientific word, to a higher unfilled orbital if energy is added to the atom. And so electrons, like we saw before, will absorb specific amounts of energy and they will jump, transition to an excited state only if the orbital that they're jumping to is empty enough for them to occupy. Okay, and so the greater distance from the nucleus, the greater the energy required for the electron to transition. Okay, and the reason why that is because higher energy orbitals are actually higher in energy. And that's very important for students to wrap their heads around. So you have to understand, we actually say that the orbitals further away from a nucleus are higher in energy because the electrons have a further distance to fall back to when they release the energy that they absorbed. You got to think of it like potential energy. So if I drop a ball, a tennis ball, from 1 foot off the ground, it's going to have much less potential energy than if I were to drop that same tennis ball from the top of the CN Tower. Of course, the tennis ball falling from the top of the CN Tower will accelerate to a much faster pace and will impact with the ground with a lot more force. And so we say the higher you are from the point of attraction or the point of gravity, the more potential energy you have. And so that's why orbitals that are further away from the nucleus actually have higher potential energy and are considered higher energy orbitals. So what is ground state? Ground state is the position in the circling of an atom where an electron can almost always be found. It's in this location where electrons, when they are not excited, are always circling the nucleus. It is from this point the electrons will absorb energy and jump to what we call an excited state. So remember, in their ground state, electrons do not emit any light. Electrons will only emit light when they're falling from their excited state back down to their ground state. And so the excited state is the orbital above the ground state where the electron will jump to, or where it will transition to. It is the higher energy level. And it does this by absorbing a quantum of energy, almost always a photon. Okay? Now remember, the excited state is an unstable existence for that electron. It does not belong there. It actually belongs in its ground state. And so it doesn't stay in the excited state for very long. When it's in the excited state, it then falls back down to the ground state and releases that quantum of energy as a photon, a particle of light. And usually that particle of light that it's releasing or it's producing is a specific wavelength, a specific color, a specific frequency of light. And that's why each one of those transitions to a different orbital will create a different color. And so, for example, an electron falling from energy level 6 to energy level 2 is going to release violet light because that's a huge jump. That's a 4 orbital jump. And so it means that the photon that it had essentially had a large quantum of energy, a large amount of energy. And remember the color variants, right? So violet, blue, those are going to be at the higher energy level state. And you have red, orange, yellow. Those are going to be the lower energy colors, okay? This image here reinforces the concept I was discussing with you. Remember that each color is a photon with a specific amount of energy. And again, the scale is from red, orange, yellow on the low end to blue and violet on the high end. And so you can see here with these Bohr-Rutherford diagrams, on the left you have violet being released. And the reason why the violet photon is being released and hitting the detector is because you had a transition, a fall, from energy level 6 down to energy level 2. That was a 4 orbital fall. If you look in the center here, you have a green photon being released. Now that green photon, or a photon with the green frequency, is released because you have the electron transitioning or falling from energy level 4 to energy level 2. So that drop of 2 released green. And remember, green is somewhere in the middle. And then you have the red colored photon. And that red colored photon was released essentially because of a transition of one energy orbital. And so each one of these colors represents a different transition or a different distance that has been transitioned by that electron. So that's very important to note. And of course, you can see in the top left-hand corner here, the absorption and emission spectrums of hydrogen. And they represent those specific transitions, those specific colors that are created because of the different jumps by the electron. The successes and limitations of the Bohr atomic model. It's at this point in most courses where chemistry teachers and physics teachers alike break the news to their students that the Bohr atomic model, the Bohr-Rutherford model, is not the current working model of the atom. In fact, there's a more recent model. But it's very important that we understand the Bohr atomic model because without it, we definitely couldn't understand the current model and we definitely wouldn't have arrived at the current model. So what are these successes of this model? The successes of this model were that it predicted and explained the emission spectra of really any atom or ion that had only one electron. However, it was not capable of explaining the emission spectra of atoms or ions with 2 or more electrons. Bohr's model was an oversimplification in need of modification. If you look at the bottom here, we have the mercury spectrum and we have the hydrogen spectrum. Now, of course, mercury has a lot more spectral lines in it because it has many more electrons. What was confusing was the band of yellow lines in the center there. It begs the question, how can there be 3 yellow bands if the same quantum of energy is emitted by electrons transitioning between the same orbitals. So if I have an electron jumping in the same area as another electron, it should be releasing the same quantum of energy, meaning it should have the same frequency of light. What's not explained here is we have three very closely related bands, which would imply that you have something in between orbitals, which is impossible based off of the Bohr model. The Bohr model suggested that you have distinct areas for electrons to jump between. And so if you have very closely colored bands in a cluster, just like you see there in the center of Mercury, that would imply that you have spaces in between those distinct positions around the atom that Niels Bohr suggested. The existence of sublevels. The large spaces between the individual colors in both hydrogen and mercury spectrums suggest that there are energy differences between individual energy levels. Bohr was correct. But those smaller spaces that you saw between the colored lines in mercury, those yellow clustered bands, that would suggest that there's something else at play. That would suggest that you have smaller differences in the energy levels. Scientists hypothesize that there are sublevels within each energy level. Each of these sublevels has its own slightly different energy, and of course that means that electrons can absorb slightly different amounts of energy, slightly different quantums, and jump to those sublevels. Now, of course, this is going to be the focus of the next package, which is entitled Quantum Theory. Okay, guys, so I hope you really understood everything we talked about today and you enjoyed it. All the best.